So the two topics I'd like to discuss are offset voltages and common mode feedback. And I'll spend most of the day today talking about offset voltages. If I have enough time, I'll start on common mode feedback. Review from last time, we, at the end of the period, defined what offset voltage was. And we saw that there was an output offset or correspondingly an input offset. And they're generally related to each other. If you divide the output offset by the gain of the amplifier, that becomes the input offset voltage. And there are two parts to the offset voltage, the systematic part and the random part. The systematic part is that the designer intentionally leaves in the op-amp. The random part is the part that is due to process variations. The designer may control that, but the designer cannot eliminate that. We have circuit techniques that can cancel its effects out maybe, but it's inherent in the design of op-amps. After fabrication, if you take an individual device, you really can't tell the difference between the random offset and the systematic offset. But if you have a large number of devices, you can look at the mean of the population, and that mean will be the systematic offset. And then from that, you could go back and determine what your random offset was on individual devices. Let's talk a little bit about two parts that contribute to the random offset. One is associated with gradient effects. So this might be the thickness of the gate oxide. And this might be the polysilicon layer sitting on top. And if you go across a wafer, you'll find that that thickness of that gate oxide kind of goes up and down a little bit. When you're processing that wafer, when you're doing diffusions, you don't have a homogeneous environment. The temperature in a diffusion furnace is typically different around the outside of the wafer than it is in the middle and so forth. And that gives rise to what we call gradient effects, kind of slowly changing characteristics as you go across the wafer. Gradient effects may be very similar to what you would have if you looked at the topography of the United States. From California to New York, through Iowa, Nebraska, and Colorado, and so forth. And as you move from the south, away from the Gulf of Mexico to the north, elevation gradually goes up. As you move from the Mississippi River to the west, the elevation gradually goes up. But if you go around Ames, you'll see that there are little creeks and valleys and so forth. It goes up and down locally as well. So you might think of the gradual a trend that takes place across the country associated with the major rivers to represent gradient effects. And then the variations that you get within a few miles or a half a mile or a quarter mile or even sometimes within 20 or 30 feet, you might think of those as more random variations. So if you zoom in on a region here, you'll see irregularities in it. And those would correspond to local random variations. These local random variations occur on dimension scales of the orders of a micron or a couple microns. The gradient effects oftentimes correspond to dimension scales that are hundreds of microns long. Oftentimes, maybe a quarter or a half the diameter of your wave, the length of your die. The magnitude and the direction of the gradients are random. Now, if you process lots of wafers, you might eventually see some correlation between position on the wafer and the gradient effects. But if you take a die and forget about where it's on the wafer and look at its gradient effects, They pretty much look like they're random. And they change in magnitude, and they change in direction. Sometimes there might be none of it present. Sometimes it might only be in the x direction. Sometimes it might be in the y direction. Sometimes it might be at 30 degrees. Okay. For short distances, the gradient effects are highly correlated. So even though they look random across the die, if you're close together and you see it going up here, it's probably going to be going up here as well, the gradient effect. Both contribute to offset. Both are random variables. If not managed correctly, both can cause large offsets. So we're going to talk about strategies for minimizing the effects of both of these random variables. I'll get a little bit sloppy, and I will use the term random to refer to the local variations, and I'll refer to the other part as gradient effects. But actually, they're both random. So here's what happens when you have offset voltage in an op-amp. You might build this non-inverting amplifier. We'd like the output to be an amplified version of the input. But if there's an offset voltage on the op-amp, the output may be shifted up or shifted down. If the gain is large, it may be the case that the offset voltage causes the output to saturate, as I'm showing on the bottom of this slide. We can reduce the effects or eliminate the effects at a given common mode input by adding an equal amplitude and opposite sign DC signal. Imagine putting a battery in series that's opposing VOS. And we'll look at techniques to do that. But this comes at significant effort and expense to take it out that way. We prefer to have the designer, even if you're going to null it out like this, we still prefer to have the designer make it reasonably small in the first place. The offset voltage is not always of concern. In many circuits, it's important that we have a low offset voltage. But there are some circuit applications where the offset voltage is not of major concern to us. Here's a typical offset distribution after fabrication. And here what I've done is I've looked at the number of samples of the population as a function of the offset voltage. And I have bins, a 1 volt bin, a 2 millivolt bin, a 3 millivolt bin, and so forth. And if you bin the offset voltages, they'll look Gaussian. Even if you include gradient effects and you have a large enough sample, they'll still look Gaussian. The mean is nearly zero, assuming that the designer does not leave a systematic offset around. If you buy parts, you'll often find a distribution that looks like this. This would be the distribution that we get if you took a process and you're going to put all of your good parts in that process into the same product number, and you set an offset specification so that during test you discarded all devices that had extreme offset values. So you'll no longer see a Gaussian distribution. During fabrication it was Gaussian, but the distribution of the sample that a customer may buy may not be Gaussian. It'd be a truncated Gaussian because the tail parts have been thrown away. Or maybe another customer bought the tail parts, and that poor customer will have a distribution that just has the tail left and nothing in the middle. So here's what might happen if you have one process run and you sort out the best parts and put a premium part number on them. And of course, now they're not in the population anymore that a customer that bought lower priced parts may have. But the customer is willing to accept lower performance parts, may not want them to be too bad, so they may be sorted again. And you might find this distribution. You might have offset voltages in a certain range negative and a certain range positive, but none with a real low offset and none with a real big offset. I found it frustrating at times in the past when I thought, well, I need a low offset op amp. I'll just take 20 parts and measure the offsets. It's not uncommon to not find any that have an offset voltage that's real small. Okay. The offset voltage is generally characterized, since it's a random variable, by its standard deviation or its variance. Oftentimes somebody will give you the offset voltage of their parts. Sometimes it's not clear in the data sheet whether they're referring to 1 sigma or a 3 sigma value. It makes a really big difference on what the characteristics are, but some use 1 sigma and some use 3 sigma values. As you're aware, if you use a 1 sigma value, 68% of your population is between plus and minus 1 sigma. If you use a 3 sigma value, 99.7% are between plus and minus 3 sigma value. So let's consider the source of random offset voltages. And the first thing I'm going to consider is a differential amplifier with a common mode input of 0 volts. So I'm grounding the gates of M1 and M2. Ideally, the left and the right sides are matched, and the output voltage is VDD minus half the tail current times the resistor R2. So I'm going to assume this is the desired output. Notice this desired output may not be 0. I'm assuming this is what I want the output to be. I'm going to initially assume everything's ideal except for R2. And R2 is equal to R plus delta R. R1 is equal to R. So the current will still split pretty much equally, even if there's a slight mismatch in the resistors. So the output voltage is going to be now VDD minus I tail over 2. That'll be the current coming to the right side times R plus delta R. That resistor got bigger. So delta V out, the deviation of V out from what we want. We wanted VDD minus I tail over 2 times R. So delta V out is minus I tail over 2 times delta R. And that would be the output offset voltage of this amplifier. The voltage gain of this amplifier we know is GM over 2 times R. So the input offset then we get by dividing the output offset by the gain of the amplifier, and we find the input offset voltage then is then 1 over AV times IT over 2 times delta R. In this case, GM is equal to 2 IQ over VXS bias, and IQ is I tail over 2. So the I tails cancel, and we see the offset voltage is equal to VXS bias times delta R over R. We talked about power affecting the gain bandwidth product in a big way. I've expressed this input offset now in terms of the practical design parameters that we usually use, the VXS biases and the power. So what can we say about power affecting the offset voltage? Jake. Power affecting the offset voltage.
Oh, no.
Doesn't affect it. Just the excess bias design parameter affects it. If you make the excess bias bigger to make the gain higher, your offset voltage goes up linearly with the excess bias. Okay. In most op amps, the offset voltage is almost entirely determined by that of the input stage. If you have a 2-stage op amp, you can get a little bit of offset due to the second stage, but usually that's negligible compared to the offset that's introduced by the first stage. So then let's consider an operational amplifier. This could be the first stage of a 2-stage op amp. One with a current mirror counterpart circuit, and the other one with differential output capabilities. I'm only showing one output, but on the one on the right, I could have the output on the left side as well for differential output. So let's see what happens. If you look at a cross-section of the device, you're going to see the impurities varying randomly with position. You'll see a variation of the oxide thickness, variation in the surface of the wafer here, and so forth. And these are local random variations that cause these effects to take place. So we know that the threshold voltage is a function of the oxide thickness and the impurity profile in the channel. If the oxide thickness is changing through the channel and the impurities are changing underneath the channel, we're getting local changes in the threshold voltage. Local changes in the voltage is required from the gate to channel to create the inversion layer. I'm going to assume that all of the model parameters we have for our transistors can be modeled as the sum of a nominal part plus a random part. So I'm going to assume the threshold voltage is equal to VT nominal plus VT random. Cox is equal to Cox nominal plus Cx random. Same with mobility. Same with W. Same with L. Now, inherent in this modeling is the assumption that there exists an equivalent threshold voltage, an equivalent Cox, an equivalent mobility, an equivalent W, and equivalent L for this device. So I didn't write it on the slide, but we're going to assume that there exists an equivalent model parameter set. So that the drain current is equal to mu equivalent Cox equivalent W equivalent over 2L equivalent times VGS minus VTH equivalent squared. Make sense? Now, there is an issue with this assumption I'm going to mention. Because this assumption is not really true. So, the way these equivalent parameters are obtained, if you think of this as the channel region, this is the channel, this might be the drain, this might be the source. And I'm going to put a coordinate axis in here, an x-axis and a y-axis. This is the length of the device. This is the width of the device. And I'm going to just look at the threshold voltage first. So I'm going to assume that VTH is equal to the integral of VTH of x and y dx dy divided by W times L. This is the integral over the channel. Make sense? The threshold voltage is going to vary as a function of position x and y in the channel. So I'm going to assume that the equivalent threshold voltage can be obtained by integrating VTH of x and y and then dividing by the area. And I'll do the same thing for Cox, same thing for mobility and so forth. Is that clear? If I don't make this assumption, then I cannot claim that there's a simple square law relationship that exists between the point variables and the model parameters. So this assumption was necessary. This was necessary to get a square law model. Now I'm going to give an example to show that this is blatantly false. And then we're going to use it anyway because it's a good approximation in most cases. So let me look at a device like this. This is the drain, and this is the source. And I've defined the channel region to be this weird shaped region. So if I didn't have this poly sticking out here and another region over here, then it would be the normal transistor. I'm going to assume these two areas are the same. I'm going to assume this area is very small on this road in between. This is kind of what they're referring to as the gerrymandering that was going on in Pennsylvania, where they were setting up voting districts that had two different regions connected by a path. Okay. I'm going to assume in this region here, the voltage is VTH. It's constant. I'm going to assume in this region, the voltage, threshold voltage is VTH1 times 2. Now, if you can imagine what happens if you have a very narrow path between this region and this region, this transistor hardly sees this region over here. There's hardly any current that actually gets out into this region. So are you with me? We can make this device. In fact, these are great ways to trim a device. You can go in and trim W or L's by doing something out here if you want to get a really, really fine trim on W and L, not something that's related to your snap size. Now, by that agreement, VTH equivalent is the integral of VTH of x and y dx dy. If I assume this distance is arbitrarily small, this will be VTH1 plus 2 VTH1. This will be times A1, and this will be times A1. And the whole thing will be divided by 2A1. And this will become VTH1 times 3 over 2, which is equal to 1.5 VTH1. So are you with me? So if I integrate over that whole region, I will find a threshold voltage that's 1.5 VTH1. But the real device essentially has the threshold voltage of VTH1. Okay? If I tried to, I can get a mathematical equation for what the IV characteristics of this are. There will be two terms. There will be a term like this, and there will be another term. I cannot write it as a single function, a single square law equation. So we're going to neglect this. We're just going to assume that there is an equivalent threshold voltage, and an equivalent mobility, an equivalent COX, and an equivalent W, and an equivalent L. So if that's the case, I can go to the square law equation and say the drain current is equal to mobility, mu nominal plus mu random, times COX nominal plus COX random, times W nominal plus W random over 2 length nominal plus length random, VGS minus VT nominal plus VT random squared, and I can put lambda effects in if I want to as well. And the expression I get for the current on the left and the current on the right will be different now, because the random parts of M1 are different than the random parts of M2, and they're uncorrelated. I could then calculate, I had an expression for the offset voltage. I can then calculate the variance of the offset voltage from that previous expression. And it's a little bit tedious because I've got products of random variables, I've got reciprocals of random variables, And if you go back to your statistics courses, you'll find that the probability density function of products of random variables and ratios of random variables is a real nasty thing. But I could do a Taylor series expansion of this and truncate. Remember, these random parts are all small compared to the nominal parts. So I can do a Taylor series expansion, and I can observe that the drain currents are equal to nominal drain currents plus a linear combination of random variables. And I can calculate these coefficients very easily when I do the Taylor series expansion. And so I then have an expression that says each of the drain currents is equal to nominal drain current plus a linear sum of uncorrelated random variables. And if I have a linear sum of uncorrelated random variables, the variance of that linear sum is the square root of the sum of the variance of the individual terms times the square of the weights. And if I do that, I finally get this expression right here, where the parameter AVT0 is a characteristic of the process. It characterizes the random variations in the threshold voltage. A mu characterizes the random variations in the mobility. A Cox characterizes the random variations in Cox. A L characterizes the random variation in the length. And A W characterizes the random variations in the width. And with the PDK, they will give you these parameters. AVT0, A mu, A Cox, AL, and AW, if you're lucky. Oftentimes, they only give you AVT0 and the square root of A mu squared plus A Cox squared. You can show that this first term is typically much bigger than the remaining terms. The first term is due to the random variations in the threshold voltage of the N channel and the P channel device. These next terms are due to random variations in mobility, in Cox, and in W and L. But for most processes, this term is negligible compared to this term. So we can approximate the variance of the offset voltage then to be 2 AVT0 squared over WNLN plus mu P over mu N LN over WN LP squared times A squared of VT0P, where these are process parameters. So what does this tell us we can do to manage the offset voltage? We neglect these terms here because they're really negligible, and this is typically the standard deviation of the offset voltage. What can we do to make it small?
The device could be larger.
Make the device to be large. This is the first thing that's cropped up now, where we have some additional design variables that have cropped into our space. Remember, we only had W over L values up to this point. So slew rate and gain and signals, everything was only dependent on W over L values. Here, they depend on W and L products as well. So we see that the area may affect things. It may affect the offset voltage in a big way. Well, that's the good news. That the area doesn't affect our previous parameters, our previous design equations. Only W over L affected those. So we can leave them fixed in a design. Now we decide how much area we have to put in by leaving the W over L value fixed to manage the offset voltage. This relationship, though, is kind of ruthless. Because if you want to drive the standard deviation down a factor of 10, so you start out with a design, and maybe you find your offset voltage is 100 millivolts. That can happen. That's too big. I want to drop it a factor of 10 millivolts. Well, what can I do to drop it a factor of 10? Sigma, let me neglect the AVT0P term, same thing applies there. If I want to drop sigma a factor of 10, this denominator is the square of the area. So I have to increase the area a factor of how much? To drop a standard deviation a factor of 10, I have to increase the area factor of 10 squared, actually. So to decrease the standard deviation oscillator voltage factor of 10, I have to increase the area factor of 100. Okay. So you start out with a small device. And the offset voltage is 100 millivolts. You say, I can take care of that. I just drop it a factor of 10. And that increased the area factor of 10, so a factor of 100. So I increase the area factor of 100. Now I'm at 10 millivolts. You say, well, 10 millivolts is not very good. I want 1 millivolt. So I can increase the area another factor of 100 and drop the offset voltage down to 1 millivolt. Now I've increased the area a factor of 10,000 from what I started with. Okay? So getting small offset voltages gets to be really challenging. Your boss comes in and says, you come in and you got a design done. You say, I've got an offset voltage, it's got a 3 sigma value of 2 millivolts. And your boss says, oh, great work. I just want you to cut it down another millivolt. From 2 millivolts to 1 millivolt. What's it going to cost you? How much space? Factor of? Yeah, a 2 squared factor of 4. So your area is going to go up a factor of 4 to go from 2 millivolts down to 1 millivolt. Okay, so be careful what you promise or agree to, because the trade-offs are ruthless in regard to area and driving this offset voltage down. So here's an example. Determine the 3 sigma value of the input offset voltage for the MOS differential amplifier if M1 and M3 are minimum sized. And if the area of M1 and 3 are 100 times minimum sized. So first, when they're minimum sized, the standard deviation of the offset, or the variance, is equal to 2 over the area. I assume that the minimum sizes are both 0.5 microns. And then AVT0, we assume the process is 0.021, and AVT0P is 0.025. Those are typical. And we find that the standard deviation of the offset is 72 millivolts, or the 3 sigma value is 216 millivolts. This is typical for a half micron process. 3 sigma value of 215 millivolts. This is a very large offset. If I increase the area 100 times, I'm going to reduce this 216 millivolts to what? 21.6. So this is much lower. Is this good? Can you buy an op amp that's got this bad of an offset voltage? If you go to Analog Devices or TI or Maxim, any of these groups are selling op amps, and you sort on offset voltages, can you find an offset voltage that's this bad? What? I doubt, I haven't looked. I doubt you'll find one that's this bad. So your boss comes in and says, we can't sell that part with 21 millivolts. We need it down to 2 millivolts. That's in the range of what you're buying, right? 2 to 5 millivolts. So then your area gets really big. Make sense? So when you look at the layout of input stages of a lot of op amps, you'll see monster-sized transistors on the differential pair and monster-sized devices on that load. That's your first stage. How about bipolar devices? You can show that, I'm not going to go through the derivations, you can show that the standard deviation of the offset is about the square root of 2 VT times the square root of some constant squared over the emitter area of the N-channel devices plus another constant squared divided by the emitter area of the P-channel devices. Again, the area of the input devices determines its offset. Very approximately, these two terms here are around 0.1 microns. So now we're going to look at the 3 sigma value of the offset voltage of the bipolar input stage. If the emitter areas are 10 square microns, that's a fairly big emitter on the devices. And we see here that the 3 sigma value is 4.7 millivolts. So these are typical values for the matching characteristics or offset characteristics for both the MOS and bipolar process. Ironically, most of your op amps that you buy, or a lot of them, have bipolar input stages. Wonder why that's attractive. What? It's much smaller. The offset voltage of this bipolar device, maybe of comparable sizes, is much smaller than that is of the corresponding MOS device. So typical offset voltage for MOS devices, after you put a fair amount of area in, are going to still end up being in the 5 millivolts to 50 millivolt range. For bipolar devices, 0.5 to 5 millivolts would be more common, unless you have extreme areas. Well, here's a theorem I just was alluding to. I don't have time. I want to talk about common centroid layouts. So I guess we'll hit that at the beginning of the period on Wednesday, and I hope I still have enough time to talk about common mode feedback circuits. Yes?
How come the offset mainly affects the first stage of the amplifier, not the second?
You can show that the offset, when it's referred back to the input, you divide by the gain. So if it's a two-stage amplifier, you take the output offset and divide it by the gain of the two stages. If the gain of each stage is 100, you divide the output offset by 10,000. If you look at output offset due to the first stage, it gets divided by 100. So if the output offset would be the same, it's divided by a factor of 100. Does that make sense? It's very much like noise. We won't spend time I should talk about noise for op amps. I'm not going to. We're also going to find the noise is dominated by the noise in the first stage for the same reason. The noise in the second stage is certainly present and contributes to output, but when you refer it back to input, it gets divided by the gain of the first stage. Any other questions? That's all for today. Thanks.